Hélène Esnault from Freie Universität Berlin, who will tell us about rigid local systems and their integrality and crystallinity properties.
Thank you very much. Is that okay with there is an echo? No, it's better. Yeah, thank you very much. Thank you very much for the invitation. And I'm really glad and moved to be in Hanoi again. I have many friends here. And it's a privilege to have friends in Hanoi. And this friendship has gone unaltered through the years. I follow with great joy the progresses of the mathematics at the Institute here and more generally in Vietnam. And I wish you success. So I don't have much of preparation here. Everything is in my brain for a good reason. Is that exactly a year ago, I started a series of lectures, which are called Algebraic lectures. That's Columbia University in New York. After which I was put under pressure by the Springer publishing company to write it as a lecture notes, and the lecture notes is going to come out in 2 or 3 weeks. So, so it is here, and I will just give a survey because we are very diverse here. If I entered into the details, it's going to be too technical. And even after the lecture notes, there is a new development, but I will keep this for another lecture at another time. So let me just give an overview here. And if I don't write big enough, please interrupt me. There is enough room here to write bigger. So what is in the background here is our ignorance about the very simple fact: if X is a smooth quasi-projective variety defined over the field of complex numbers, then we know that we can associate to it the underlying topological manifold. And then in broad generality, we can ask what distinguishes this complex manifold from any kind of complex manifolds, what properties. And most particularly, and usually when we have a complex manifold, we look at the homotopy type. And the first invariant of the homotopy type is the fundamental group. So we look at the fundamental group here. And as we know, a fundamental group is defined once we fix a base point, but it's quite irrelevant what base point we fix, because if you fix another one, then the two so-defined groups are isomorphic in a precise way, but nonetheless, I'll write it for a second here. And what we know here is that the homotopy type of the underlying topological manifold, let us assume it is connected here. It's a finite CW complex. And because it's a finite CW complex, it's the same as saying that this group here is finitely presented. So finitely presented means finitely many generators, which are given by the one cells. And then finitely many relations, which are given by the two sets you glue on the one cells. So then you can already restrict a little bit the very, very general question we had before. Among all finitely presented groups, what are those which are the fundamental group of the underlying topological manifold of a smooth quasi-projective complex variety? So this is an extremely ambitious question of the type like a Hodge conjecture, what cohomology classes are coming from algebraic cycles or whatever. You cannot, given the group, how can you reconstruct a variety? It's impossible. So we look for obstructions. Is that big enough? So we look for obstructions. This is one way to think. And another way to think is to say, okay, this group is very difficult. I'm going to analyze the group via its representation category with values somewhere. I mean, more generally, you can say with values in an algebraic group, or you can say with values in a reductive group, or you can say with values in GLR. And then with various coefficients. And then, as always in algebraic geometry or arithmetic algebraic geometry, you can say, I do that at the level of the representation category, or you can say, I attach to it moduli spaces, the points of which parameterize precisely those subjects, and I look at the geometry of those moduli spaces. So let me write here. So this is another way to think. You can look at the representation category of phi1 with values, and here we are going to look in the first step GLRC, or if you fix an R, I mean, when you look at the category, you don't distinguish really the R, they are all mixed, but a more geometric way to think of it is to look at the moduli space here, which is usually called the character variety. It's a very old invariant. It's a long time people constructed the character variety here of phi1 with values in GLRC. And now you see this point here. I have written it because it's part of the construction. But when you want to understand the topology of the manifold, the point plays no role. And we said that the pi1 is independent of the point up to isomorphism, in fact, in a precise way. And this translates into the fact that we don't really look at the representations here. We look at the representation modulo conjugacy by elements in the target group. Or here we look at the character variety, the points of which parameterize representation modulo conjugacy. And a representation modulo conjugacy is called a local system. So let me write this. Let me finish my sentence. Modulo conjugacy. And modulo conjugacy, this is called local system. And this character variety here, which is constructed by choosing a point, defining a so-called fine moduli space associated to this, it's called a frame moduli space. And then because we mod out the choice of the point by the conjugacy here, it's a GIT quotient, and that is the answer to Garber's quotient. Then the complex points of these are representing isomorphic classes of semi-simple representations with values in GLRC, semi-simple local systems. And we can also look at the irreducible ones, or we can look at just the semi-simple ones, and I don't need any decorations here because this is a definition. So this is a general thing. And before I proceed, let me remark here that before we enter into the beauty of the topic here, let me remark that in doing so, we ignore a very important invariant. Which is like this, because phi1 is finitely presented, and in particular, it is finitely generated, then any representation here with values in GLR, let's say of C, has values in GLR of A, where A is a ring of finite type over C, because it is finitely generated. So there exists a factorization here. Let's say rho A. And this is finite type over Z. But now any ring, a finite type of a finitely generated ring, a finite type over Z, has a ZL point, an L-adic point for L large. So this embeds into GLR of ZL for some L. There's some embedding like this. This means that in fact our original complex representation here can be thought of as this representation here, but this representation, because ZL is profinite, it factors through the profinite completion of the fundamental group. So it factors. So there exists a factorization. Let me write rho hat here, where here it is a profinite completion. But now the profinite completion of the topological fundamental group by Riemann existence theorem, which is telling us that the topological cover of the complex point of an algebraic variety is in fact algebraic, and the cover itself is étal, finite étal, then this group here is the étal fundamental group as defined by Groechenig. In fact, Galois and Groechenig, so to speak. So let me write étal here. Or I don't write étal, I just write the scheme over X. That's the étal fundamental group. So that gives us a topological representation, a continuous representation with respect to the profinite topology on the left and on the right. And this is called an L-adic local system. I mean, up to conjugacy here, it's an L-adic local system. So that's the first information, which is maybe nice because it goes in direction of arithmetic, but there is a bad point here in this information is that it also tells us that our complex local system here ignores the kernel of pi1 to its profinite completion. But so the local system L, which is a representation up to conjugacy here, ignores the kernel of pi1 to the étal pi1. But now Toledo, a while ago, in an absolutely spectacular work, which answered the null question of Jean-Pierre Serre, showed that this kernel is non-zero. It might be non-zero, in fact, it might be huge. So all these viewpoints here, which was here, ignores completely this fact here. But nonetheless, we will see that it will yield an obstruction here ultimately. So let us come back to the moduli here. So which was a character variety. And as we said, this character variety here, its complex points are isomorphic. So maybe I should write it here. So the complex points here are iso classes of semi-simple local system of rank R. So that depends really only on the fundamental group. You don't see any analytic topology of X. You don't see any algebraic topology, no Zariski topology. But if you start putting conditions at infinity, so if X is not proper, then we can be more ambitious. We can prescribe, so it's not proper, so it has a good compactification, etc. And then for any divisor, irreducible component of a good divisor at infinity, Then we have inside of the fundamental group here, we have what comes from loops along the branches of the divisor at infinity. So we can also prescribe, for example, we can fix quasi-unipotent conjugacy classes for any di where d is x bar minus x is a normal crossing divisor. Let's say strict normal crossing divisor. It's a conjugacy class inside of GLR of C. And then now we need really the structure of the scheme in order to define this. And this is the reason why here we change the notation. We look at the so-defined modular space. We no longer call it character variety because it depends on more than just the fundamental group. It depends also on the structure which enables to tell us, which enables to fix some elements here, which in geometry are coming from infinity. So we can we say X, R, the R we had before here. And in addition, we can fix those conjugacy classes, let's say Ti. And then we can also fix a determinant. And I'm going to fix delta here, which is the order of the determinant of the local system. Delta, it's a finite order of determinant. So this is a modular space. And now, so we are here about the years 80s, and comes the work of Carlos Simpson. And in his huge monumental article published with the IHE, publication of the IHES, where he develops the so-called Simpson correspondence. Then he devotes about 1/3 of his huge article to rigid local systems. So let me define it. Once you have these definitions here, this modular space, I think of it as being a modular space over C in the first move. Then it's very difficult because it's I forgot to say it's affine. Well, now it's no longer affine because I fixed something here, but it's finite type over C, and in fact it is finite type over OK, where K is a number field. Which contains the eigenvalues of those TIs here and delta. So it's a small extension of Q. And then, so over C characteristic 0, then Simpson considers a rigid local system. Which are precisely, I think of them as being complex points of the moduli here, and they are the zero-dimensional components. So I abbreviate here this big notation here by M. And then because it's a zero-dimensional component and the whole moduli are defined in particular over number fields here, then we know that they are defined over T bar. And now if you remember the definition of this modulus, this means that the underlying representation of the fundamental group is defined over T bar. So I just write by one here in GLR of Q bar up to conjugacy. And then, of course, when you have a modular functor here and it produces isolated points, then you want to say that they are isolated for a good geometric reason. And she postulates, and this is really one of the central conjectures in arithmetic geometry. It's a conjecture of Simpson. Postulates that they come from geometry. So rigid implies geometry. And what does that mean? That it comes from geometry? So some other people would say they are motivic. That's the same mathematical content. So it means the following: that if we have X here, then we find the dense open. Open is a risky open here, maybe I should write it. There is a dense risky open here with properties that is endowed with a morphism from Y, which is smooth projective in such a way that when we restrict our local system, then it comes from the variation of the relative cohomology of G. So that means it's a subfunction of R dot G lower star. So this is called a Gauss-Manning system here. And by the, of course, absolutely fundamental work of the linear, we know that subquotient here is equivalent to say split, so summate. So this is a so-called semi-simplicity theorem of the linear. So, so that means geometric. So, for example, if the monodromy is finite, so that means the image of the representation is a finite subgroup of GLRC, then you could take this Y to be a finite étal quotient in fact of the whole order. So that's the first geometricity notion, and then it is an extension of this, because to say that it's finite étal, it means that it's proper and smooth, and this is this. And then why do you restrict here? First, you want a nice categories. It's basically process to restrict to some dense open. And you can see that in geometry, for example, think of the moduli of curves. Then you have the smooth moduli of curves. You have the smooth in the sense you have the universal curve, which is smooth. And then at the boundary, you also have the points where the curve is no longer smooth, but it's a tree. And that doesn't change the fundamental group. So that doesn't change the local, so it's a Gauss-Manning local system. So then you extend a little bit your boundary, so that means that it is the boundary and that it is the open on which you have the genuine split. And then so to speak, documented that the big conjecture is not completely out of the blue by two theorems. One is Varieties Simpson Simpson's correspondence. At least it takes if there is no boundary condition. So let us assume here, just for the discussion, we can generalize, but it's a survey here. X is X bar. Then one of the key features of the Simpson correspondence is that associated to this M here, there is a so-called M tips, or maybe it's called sometimes Dolbo, which has a property that it's again, so now it's really defined over C. In fact, it's defined over the same field of definition as the variety set. So the field here, this case here has to do with the coefficients of the representation, and the field of definition here has to do with the field of definition of the scheme here. And this is again a finite graph, and the complex point of that are so-called which are very popular in Vietnam because of Ngo Bao Chao. So it's a linear here operator, which is integrable. So if you do it twice, it's going to be 0. Okay. And so because we look at the moduli again, it's going to be so much simpler in the one. I don't go very far in the discussions here. And this is really constructed by our GIT, so those are stable or semi-stable. And I don't go into the details. There's one semi-stable here. And then it is endowed on this side here. So it has two remarkable features. One is that it's endowed with an algebraic action of TF, which we call a flow here, which multiplies the Higgs field by T. That is called the Higgs flow. And Simpson proves that the fixed point of the Higgs flow here are, so we can write a fixed point, are a complex polarizable variation of hot structures. So it looks very technical here if you are not in the topic, but at any rate, if a local system is coming from geometry, then it has to have this property here, which is coming from the variation of the hot theory of the cohomology of the fiber. So this is certainly one, and the second thing proves here, which is really extremely profound, is that this is, if you look at the complex point on this side and the complex point on this side here, it's a topological isomorphism, and in fact, more is true. It's a real analytic equivalence. Most particularly here, if you, even if it was only topological, if you have isolated points here, this gives you isolated points here. So now, if you plug in your GM flow on an isolated point, it's fixed. So that means the conclusion of Carlos Simpson here is that a rigid local system underlies a complex polarizable variation of hot structure. That's the first, so to speak, incentive to propose a very big conjecture. The second incentive to prove is of arithmetic nature. You remember that our local system here is defined over two bars. This is a group of finite type. So in particular, outside of finite points of the field of definition, the representation is going to be integral. So to put right here, it has values here in OE, let's say in the number field. Once you invite finite field, so you could take an L here, which is not the divisor of L, then complete at this point and make it an analytic local system. So to go here, you assign an analytic local system as explained. In fact, as we explained before, even if it was not rigid here, we would not know that the monochrome is defined over two bars. Then we could take this general consideration we had at the very beginning, and we can make out of it an analytic local system. But here it's very precise. And then it proved that this OL here, so this OL now is a local system of the étal fundamental. And but it proved that this local system in fact is arithmetic. And let me say what arithmetic is. And arithmetic means what you expect if it again comes from geometry. It means that if it comes from geometry, so I think our diagram was already here. When you have such a diagram here, this is defined over a field of finite type. The open is defined over the same field of finite type. It's smaller to be defined over the same field. This morphism is defined maybe over a larger field, but still a field of finite type. So it will be the case that the L-addict Gauss value is going to be definable to the final part. So that is to say that these local systems here, factors, as a local, not as a representation, but as a local system, the modulo conjugacy, it factors in the so-called arithmetic local systems. So F is a finite part. And it proves that. It's a very beautiful theorem. It's not so hard to prove. So this is under the assumption that the points which are the isolated points here was only always under the assumption that we look at the irreducible part for the consideration. And his thinking was like that. His idea was like that. You look at the action of the Galois group of F acting on the moduli space of local systems. You have the Grothendieck's homotopy exact sequence, which represents the Galois group of the ground field as a quotient of the arithmetic fundamental group by the theoretic one. So that means you have an action on when you take a point, a representation here, then you can let the Galois group act on it and find a new representation here. And then he argues that if it was not the case that it's arithmetic, that if it's not fixed by it, it's going to move formally at the close point of your moduli since local system. But the local system is fixing, so you can move it at the first order, at the second order, at the third order, but you cannot move it along the whole gamut. So that's a very beautiful argument, which is keeping things on. Of course, you have to make it work, but so those are the two theorems. He proved himself as, so to speak, a background for his proposal. So now he mentions himself. Mentions himself that if the he mentions, in fact, and it's very precise, he said that in order, he said himself, I apologize, that this geometricity here, of course, is completely unreachable. How can you prove geometricity? But he said the most important part of it would be to prove that those rigid local systems are integral. What does that mean? If it was coming from geometry, now we go back from the analytic theory, we come back to the transcendental theory. If it's coming from geometry, you remember that the local system is coming from the variation of the cohomology of the fiber. And when I say cohomology, I didn't say which cohomology, that's a Betti cohomology, but the Betti cohomology is defined over C. So that means this local system is defined over C. So when you take a subquotient, it's going to be defined over C bar. So he mentioned that the motility, the geometricity conjecture lies the so-called integrality conjecture. He poses it as a separate conjecture. I.e., it means that if L is rigid, as I said, but maybe not so clearly, so let me write it again. Rigid means in particular it's an irreducible local system, then it forms from a row its values into LR of C bar. C bar being the algebraic integers inside of C bar. And because it is irreducible, this is equivalent to saying that express functions which are defined by the characteristic polynomial. Sorry. T minus 4 acting on the fiber at the base point of the fundamental picture lie after differences in that. So this is clearly an arithmetic problem. And as a matter of fact, there have been many attempts since the conjecture. So the conjecture was, I think, was presented at the ICN in Kyoto. To solve this problem by L2 methods and p-additive methods on the trees which are associated with this topology. So now, okay, so maybe it's time to say something. Yeah, okay, I leave it like this, and let me continue. It's a fairy tale, if you believe in this. So one direction to go is precisely what I explained, which has been, again, explained by Simpson himself. Now, there is another direction to go. And in fact, let me say that this conjecture here, geometricity, so the integrality conjecture. So at the end, geometricity implies integrality. So that gives you, if you like, you can separate the conjecture. That implies integrality. It implies integrality. So another direction to go is the following. You can try to think what would be other consequences of the big conjecture here. And we know by the Riemann-Hilbert correspondence, the complex Riemann-Hilbert correspondence, maybe we should say Sofia Kovalevskaya Riemann-Hilbert here, correspondence. We know that the study of the local systems here is equivalent to the study of the underlying connection with the white blah for the algebraic connection. So that means if you go back to the general picture here, which was somewhere on the board with the modularized spaces here, you can add another one as a triangle, which consists of the so-called Johan moduli, which is defined over the same field of definition as a scheme. So from here to here, it's defined over the same scheme. And the complex point of this are semi-simple in our life, which are irreducible, which are the right. So you can try to think of it and to draw conclusions of the speed conjecture on this modular. And again, by the deep theorem of Simpson here, by the Simpson correspondence, under the same assumption as here, that there is no boundary here, there are generalizations, but we don't know from this. Then to go from here to here, this is the Riemann-Hilbert correspondence. So this is complex analytically an isomorphism. To go from here to here, then because this one was real analytically an isomorphism, this one is real analytically an isomorphism. So to study isolated points here and here, as already mentioned, it was the same, but we can also think of it as being here. And now there is one thing we can do, and it has been that one aspect of chaotic Hodge theory is to say, because X is defined in part over a scheme of finite type over Z, and so is in Nabla, because in Nabla is a connection. So this is defined over a field of finite type, and then a scheme of finite type, or let's say affine here for simplicity. And so is in Nabla, so it's defined here. And then to underline that we think of it over S, so let us write S. And then we can restrict this, so we can take S that it has really good reduction. And if we have boundary conditions, then we assume that we have also good reduction for the data of X inside of its good multiplication, and also good reduction for the connection. So there's no force in above S for the connections. So we have a good reduction. So in particular, so for example, we can restrict to the open here when this morphism is loose. It's just for convenience, but also technically, even though I will not enter the details here, I can only argue on schemes which are unramified. So we can take double points. So W here is the ring of the vectors over a finite field here. So we can restrict our whole data here to W. So I shorten the notation like this here. So this is a connection which is no longer in characteristic 0, it is in non-equal characteristic, so relative to W. And we can try to think what would be the properties of this EW here if it was a case that was geometric. So you would like to say, and in fact, I think historically is the first instance of those theorems goes back to the linear when it proved that if you have a Gauss-Mann linear, then in the modern terminology, the Gauss-Mann viewed on the downside here, like this, then the Gauss-Mann is viewed as a connection on the scheme over the unramified scheme over the W, defines the F as a crystal. So let me write. So EW. So if we have so we found that if the initial object L or that is reaching, then it will be the case that the EW has defined force here. The W is an F isomorphism. I should not say W here, I should say capital K. And now there's a confusion with the initial capital K. Let me write the field of fractions of W is an isocrystal. So let me explain this. So maybe I go here. So I see. Then the connection over the field of fraction of W should extend to the connection over W. That is not given by the geometry here, so there is no new information because I constructed it like this. That's the first information in this terminology here. And then the second information is like this, that this field of fractions here, this connection over the field of fraction is invariant under action of a power of the probability. So now, of course, when I write that, you can stop immediately. What does that mean? And that is enough for the whole terminology. So there's another way to present it, but let me make a remark here. We know what is the probability on the material reduction of our scheme. So when we take our connection and we look at the material reduction, we know what is the probability pullback of this connection. So at least modulo P, you know what I'm talking about. But now it's not the case that this action of probability on the spin modulo leads to an action of probability on X over W. But because we have good reduction, it is a case locally, formally, on the scheme over W. So locally, formally, you can say what is the probability pullback of the connection. And now you have two ways to go. One way is to say, I know that my E nabla over the volume defines an isocrystal. I haven't yet defined what it is. Just take it as a black box. If I know that, then I know that this local lift of F and then the probability pullback of my connection is going to be independent of the choice of the lift. That's one contingency computation. Another way to think is to say, I do not know that my the way I presented it, I do not know that it defines an isocrystal. I just have a connection, but with the information that the connection has this model over W. Then this is still the case that I can take locally, of course, I can take the pullback of the connection by a little probability. And now a very nice computation, which I learned from Johan de Jong, but which goes back to Pierre Berthelot, is that at least if the residue characteristic is 3, the radius of convergence of the exponential function is going to tell us that even though I don't know it's an isocrystal, it is the case that those probabilities are independent of the choice of the probabilities. So we have two ways to see. So you assume the residual characteristic is at least 3, that probability is just 1. And then to say that it's an F isocrystal here is saying that it is stabilized by this operation, maybe not the operation itself, but maybe the finitely unified. So that is one thing. And now the isocrystal itself, we can define it independently. So maybe I just write here. Isocrystal, one purely algebraic way to say is that we have this connection. So we always need the model. We go to the material reduction. There is a so-called P curvature of the material reduction. The P curvature measures in as far the mod P connection is spanned by flat sections. And to say that the P curvature is nilpotent is saying that the connection, the material reduction of the connection is filtered in such a way that the gradient associated to this situation has the property that it is spanned by flat sections. That is equivalent to saying that the curvature is nilpotent. So because it's technical, I don't enter into the details here. So you expect this. This is true. And why do you expect this? It's because I think the as a person, then it becomes a whole topic, one aspect of the topic of periodic hot theory. The Gauss finding has this property. Another property you expect which is analog. So it's a nice, I stop here. I would not be able to talk on the instruction, so it doesn't matter. So another property here is to say, when we do complex geometry, we know that when we have a smooth projective of this here, the variation of a structure is a variation of Q of because it's smooth. So the analog, there's an analog statement on the p-adic side, which says that if we look at this isocrystal here, it has specific properties, which are, so to speak, which mimic in some sense, or which are analog in some sense, to the fact that the variation of structure is a variation of Q. And this notion here is a notion of crystallinity. And there are two ways to speak of pixels to their calculus. One way is directly on this connection, on this isocrystal. This isocrystal simplified, like the variation and this situation has a certain strong divisibility property, which I clearly don't want now. This is one way to see. Another way to see, again, this is called a Fontaine-Lafont unity, which was developed by Fontaine and Lafont. Another way, these sound properties, as I said before, is to think of the associated p-adic Gaussian, a p-adic local system, and to say this p-adic local system has specific properties. Now it becomes very technical to write the specific properties. Gerd wrote directly threshold pointer from one notion to the other in such a way that for today we can see only on the Graham side, the crystalline side. So we write here crystallinity of the underlying p-adic property. So now it's time to write a few theorems. And unfortunately, I will not tell you the new obstruction we obtained with this kind of thoughts here. So what I write here, those ones are these Michael's. So the first one is integrality conjectures here. And we need here a tiny extra property. You remember that reaching means an isolated point of the moduli. So now if you have a scheme of finite type and an isolated point, then you have two options. Either this point is smooth, okay, this is one, or it's not. And the proof we provided here relies on using the fact the proof works only for smooth points. So this is called cohomology derivative. I mean, we call it like this now, everybody calls it like this. It's very hard to find which local systems which are not cohomology. Because, for example, in dimension 1, since the book of cards on the local system in dimension 1, they all are cohomology. But finally, with Johan and Michael, let's take an example here. And two, you see, F isocrystal property. And three is crystallinity property. So I should be more precise here. And let me, so here I already put restrictions here. So I don't have much time to be more precise, and I don't have much time to tell you what is the new obstruction for a group of finite type to be a fundamental group of smooth quasi-projective variety of the complex Laplace. it's too bad because you will see that this abstraction combines both the arithmetic length program and the geometric length program. This is quite heavy. But I can say one more here is that this proof here relies entirely on the arithmetic length. More precisely, we should say, but I don't have much time, it relies on this very evolutionary idea of the lead in Witt, where she predicted at the time of complete absence of the electric program, it predicted the existence of the co-compilers. That means compatible local systems for all n. The moment they are arithmetic on, it was predicting on any normal variety defined over finite field. That is not yet true, but it's true on smooth variety defined over finite field. That means if you have an arithmetic local system which is irreducible and I don't know, you have a notion of compatible local systems. So you take knows that probability of all close points, their conjugacy classes are dense in their fundamental. So to know local system, once you know it exists, you just know in quotation mark. You just have to know it over those points. And then you have a notion, of course, of twist of a local system. If you define an algebraic isomorphism between 12 bar and 12 prime bar, then you can twist the coefficient of the local probability. So then the prediction of the linear, which is absolutely breathtaking, is that once you have an analytic local system which is arithmetic, then you have an L prime analytic local system which is arithmetic, and with the properties that the local characteristic polynomials are obtained this way. And that has been proved by Freie in rank 2, thanks to this proof of the length correspondence in rank 2. Then by Laporte, using just defender, and moving arithmetic local system in higher rank, holds up on a curve, the normal curve with finite. And then higher dimension by a quite spectacular form of defender, but on which works only in quotation mark for X being smooth over Q, reducing with an extremely clever argument to the case of curve. And in practice, clever arguments stems originally from the good Bison, who unfortunately after we developed so that is this. So this is really purely arithmetic, and so two properties here, which developed here, are here. It's so now we have a new proof here, which is purely we had a proof which was going through the material chunks here, and doing algebraic geometry and an imitation of the sixth flow, which I explained in details here. But over a finite field, the method which is true essentially to transfer with collaborators. And in a few days, the technique should show up on the area. We have a purely PID group which relies, in fact, on topology and notably on properties which have been analyzed and proved by institutes. So that is for the two things. And I have another 2 minutes here, and let me just write the box. Is that if you look at this multiply, but now no longer over C here, but you look at, so when is the Betty multiply here, when we look at the Durham multiply over the whole line here, we obtain those Durham properties which are written here. So this is like the Durham or crystalline properties here. Here is like the Betty or like the multiply. But now you look at the Betty moduli, but it's said to look at the final definition. it's defined here. And now you try to analyze not the zero-dimensional components here, but the higher dimensional components. And it turns out that you cannot do anything except one thing, is that you can show here that using this object of just as geometry and going to a characteristic which is very large here, that means you see bigger representations here as a large residual characteristic identity, then you can apply the so-called De Jong's conjecture very far. And De Jong's conjecture, I don't write it, even though it's very beautiful, predicts the following. If you have a spin now not over C purely, but again over a finite type, then it will be the case, the formulation is different, but it will be the case that if you assume you do have an irreducible L-adic representation, geometrical, you assume you have a geometric L-adic representation or local system which is irreducible, then it will be the case that there will be of a certain range. There will be another one which is arithmetic. And this is the first thing. And using this plus some method I explained, which we developed, it enables one to define a very simple new abstraction for the group of finite presentation to be the fundamental group of the complex variety. And the property is the so-called Witt probability. When I stop here, I have one minute to define. Yeah. So let me, and I should say here that's the work with your hand. So let me give you the setup and send it to you. You can do nothing. So again, consider now the north of the piece. The hand side, the crystalline side, you look at the political side, and you look at the so you look at the multiple space at just one end here of those complex local systems which are reducible in the given line and maybe some declarations at the political complex. And here this is over and along with what would be so again, the complex points here are irreducible ones. I just cut out the irreducible ones in characteristic L. Now, what you do here, it's a scheme of finite type. That's all you know. That's precisely why I started the lecture. We know nothing of the fundamental group. It's a scheme of finite type. So if you take a point here, this large characteristic, it will be the case that the fiber here. So this small piece, we know nothing, but we know, let me explain differently. We know that if we take the underlying vector scheme, it is numerical scheme. Okay? So that means if you take L here, which is large enough, then up to taking the underlying vector structure. So you can take a close point, and this close point this corresponds to the representation here of the topological fundamental group, optical legacy LR of L bar. Okay? Like a finite extension. So now what you can do is you can complete formally your moduli at this point. This idea of computing M at a closed point like that, we are not the first one using this idea. The first one is Trinkel when it proves that the Kashiwara, that the Taylor conjecture of the facet the same time implies Kashiwara's conjecture of the field. So you can complete here. Okay, so you know nothing except that you put yourself in the situation where the underlying matrix structure is here. Now, here you just have a residual representation. Again, because my use is the finite extensions here by the very definition. So the monodromic group is finite. Now, by Groechenig specialization theory, you know that these representations here is going to factor through pi 1 of x and bar for p larger than the cardinality. Like what this one. Fundamental group over C. This one is subjective. And then so you have a factorization like this. This is Groechenig. Because Groechenig is telling you that the specialization group homomorphism is an isomorphism from the pro and so now you see it becomes once for this P large here, you look at the model now of X over P bar, and you have this residual representation. And now it is a case that once you have fixed this one, the computation of the moduli functor is going to tell you that the formal computation you have here is precisely on X over X bar, the deformation space defined by laser, which is residual representation. Now we are at the framework of the De Jong's conjecture because De Jong is telling us, and because the point was chosen here generically, so to speak, generally, then this is going to be, so then that's the formal schemes here, which you can think, so this is a part here, that's a formal scheme, and then De Jong's conjecture is telling, so it is the underlying reduced structure is this. And then De Jong is telling you, I mean, the conjecture is, De Jong is telling you that, so we have a point here that is telling you that this is here for an arithmetic system. That's De Jong's conjecture. And De Jong's, okay, that's it. And De Jong's conjecture has been proven by Shekar Carré and Gephardt-Butler in specific cases. At the beginning, when it came out 20 years ago. And then but by methods of arithmetic geometry, and then by Dennis-Getz theory, using the geometric length program under the assumption that the L is at the speed. Okay, so that means we obtain here an arithmetic representation on so assigned to this here. This is residual representation. So now that's how we use it because now we have an representation over S2. And now we lift it to C as a representation coming from F2, from X over F2. And over F2 now we can take the Lorentz companion. And the Lorentz companion is the way we plot the notion of integrality for the fundamental group. And I can spell it out just in words. the Witt integrality is telling us that if in the rank R we do have an irreducible finite determinant local system with quasi-independent Laplace infinity over C, then for all N we will have one. And then it's easy to produce, and this is has been produced by Hélène Esnault and his collaborator, to produce a finite presentation group does not happen. I don't know if this is good. Well, stop. So, number, well, in fact, now, written here is for the exporter, in all generality. Now, for the crystallinity property, the way I presented it, it's just, you know, it's this crystallinity property. There's something which is regarding the wall involving manufacturers. I was telling you, you are assigned to the Johan object, you are assigned a crystallinity. This is part of W. So, but then, if you want to use the part which is number and is using, you have to go from this precise representation, which by the very definition is defined over X over the TLT on modified TLT to X over CP bar, because you want to compare it to the complex local systems coming from X over C. So you have to prove that your crystalline representations, once you go to CP bar, they don't collapse. I mean, it's a one-to-one point. Set differences in ones which are defined about 50 bar, which one to see. So the set is this one, it's a different. And for this part, this is a article to use it, which is not to say you really use it, you can use it because not, but as written like this and presented like this is the problem. But if you again, if you want to run this part to a pretty local system of the C, then so far that you need to it might change this is classified. We probably haven't seen it. But I want to insist that using your topology which you expect, and I give you about points and system properties now, which is you can develop the assumption we won't come to